Good afternoon, everybody. I'm Logan Riney. I'm from the University of Louisville in Louisville, Kentucky, and my advisors are Dr. Yunzek Shum and Dr. Jacques Amar. Today I'm going to be talking about temperature-accelerated dynamics, simulations of copper-nickel 110 growth. So here's just contents for what's going to be covered in the talk. So why am I studying this? The evolution of surface science over the past few decades has enabled the creation and investigation of materials on the atomic scale. There have been discussions about materials such as nanowires, nanostripes, nanoclusters, and nanodots. Another thing that has been looked into is atomic intermixing on surfaces of material and how it plays a role on the formation of structures. So the motivation behind what I'm doing comes from this paper that was published in 2008 of a copper-nickel 110 growth that they did in a lab. As you can see, this is a zoomed-in version of this image right here, and you can see these dominant stripe formations occurring. And so here's a copper stripe, and it's about, I think it layers up to about 3 copper atoms, and then below it is the nickel substrate. And as you can see here, there are these vacancies, the little darker portions of the image. But the reason why this is surprising is that they noticed intermixing between the copper and the nickel, and there's no intermixing between 110 and 111. So here's an example of a 100 and a 111. And then here's what I'm going to be talking about. So why am I doing this? To figure out the mechanism of intermixing and then find out the effects of surface defects on the intermixing process. So what I'm going to be using for my simulations is temperature-accelerated dynamics. Classical molecular dynamics allows fully realistic simulations, but the problem with it is that the timescales are way too small to see activated events. So Sorensen and Voder came up with temperature-accelerated dynamics, which takes your system, raises its temperature in order to show these activated events, and then records the time of the event at the high temperature, and then uses this Arrhenius equation to extrapolate down to the low time for the event. And this actually accelerates the speed by a factor of about 1 million. So here are the 2 substrates I'm going to be covering. One perfect substrate where there are no defects, and then defected, one with vacancy defects. So there's like a defect there, here. So the type of, I'm using empirical EAM potentials, which are many body potentials that take local electron density into account. I'll be using AFW potentials, which are a set of potentials that basically are in better agreement with DFT calculations. And the way it'll be growing is through deposition at about 0.23 eV. My deposition rate in my simulation is about 1 monolayer per second, while the experiment that I'm basing my simulations off of has a bit of a lower deposition rate. And if I were to be using MD simulations, the deposition rate for that's about like 1,000 monolayers per second. So that's why this deposition rate is optimal for this kind of simulation. So here are plots of one of my systems as a function of its coverage. So as you can see here, the blue is the nickel and the yellow is the copper. And as you can see, right here is a first embedding, and then here is a second embedding in the material. And basically, this just shows the formation of certain structures. So as it continues all the way to 1 monolayer, which is basically just like you take the first or the upmost layer, and then figure out how many atoms are in that layer, and then 1 monolayer is an additional layer to that. So as you can see, this dominating structure begins to form. And so here is a coverage plot for a simulation that has surface defects. So here in the red circles, there are missing atoms. And basically, as you can see, by the time a third of the coverage happens or is deposited, all of the vacancies have been filled by the motions of the copper atoms. And then certain structures begin to form here. So comparison with the experimental results. So as you can see here, the fraction of embedding as a function of coverage continues to rise as the temperature of the simulation rises. And you can also see that the defected surface also increases that. And the reason why it flatlines is because my system size, basically because it's so small, it saturates over time, just due to its size. And also, as you can see, the more vacancies there are, the more embedding there is. So I found a couple embedding mechanisms. The first one is a single atom embedding, and the energy for it is much higher than this nearby atom-mediated embedding, as I began to call it. The main pull from these two embedding mechanisms is that this one's more energetically favorable, because after the embedding process happens, the relative energy is lower. And so at 300K, we can, or when the simulation's done at the temperature, for this one it was 200 and this one was 250, you can extrapolate to room temperature, which the experiment was done at, and we can see that this event occurs every 68.9 microseconds, this one 13.3, which means that this one happens more often than this one, and it's more energetically favorable. So here's a small animation of how this process takes place. Two copper atoms are in adjacent rows of one another. So this is a two-step mechanism that is energetically favorable. The energy for this event is 0.45 eV, which will happen at room temperature, and it's the dominant embedding mechanism. And so we wanted to take a look at possible strain effects in the system caused by this embedding, considering that the copper atoms are larger than the nickel atoms. And so as you can see, whenever an embedded atom, or whenever a copper atom has been embedded, atoms are more likely, or the activation barrier is lower for atoms that are moving away from the embedding site in pretty much every case. And so this could be a result of strain in the system, and it could also help us understand how these stripes form because of the nucleation sites. So some conclusions. Nearby atom-mediated embedding is a prominent mechanism which intermixing occurs. Embedding increases with increasing temperature and the density of vacancies on the surface, which is consistent with experimental results. And strain also appears to play a role in the clustering of the atoms, and larger system sizes need to be run in order to reduce the finite size effect. That's all.
Any questions for Logan?
So the general thing that's happening is like you have two sizes of balls and you shake them, and then the smaller balls go to settle down. Is that sort of what's happening?
Well, actually, the copper atoms are actually larger than the nickel atoms, but they,
According to my model, they would go up.
yeah.
But it's the density that matters. Or the
Just the main thing is that the embedding process is more energetically favorable when there are two atoms near each other whenever the embedding process happens, rather than just a single atom. And then this makes more stable bonding structures.
Are you just depositing copper?
Yes.
You're not putting any additional nickel?
No. The experiment was just a flat nickel substrate that they annealed to get rid of, or to make it flatter, and then.
Can we go back to the picture? So, those are surface pictures, right?
Yes.
So it's not touch with the material, that's the surface after some amount of deposition.
Yes. And so you can see that these nearly like 1D structures begin to form on the surface. And then, like I said, this is a zoomed in.
And you don't have a large enough size yet to get that 3-atom base or not?
Let's see. So using the simulation that I did, it took about a month for one layer to be deposited on the system. So I need to wait a bit more just to see how the system progresses, and then I'm going to work on making larger systems. Well, I do have a couple larger systems that are running right now, but the calculations go is in squared, so it's really.
So I understand that for your simulations, you increase the temperature to increase the kinetics of the fusion processes and the deposition processes, right? Did you verify at all that by changing the temperatures, you weren't changing some of the underlying thermodynamics?
I'm not sure on the specifics of that, but basically it would stop extra. This is just a small diagram, but it would just stop extra events from happening. That's just the nature of it. And like the beauty of it is that many events can happen, but it only stores or it only accepts the events that are within your parameters. So you see events that are really high energy and less likely to happen, but it's not accepted into the simulation. If that makes sense.
So the answer to your question is yes, the thermodynamics is correct. It is taken into account in the temperature accelerated dynamics method.
Any other questions?
All right, let's thank Logan.